Yeah, I'm going to approach this in a slightly roundabout way to maybe give you also a bit of an idea about how we try to approach developing Lean at the FRO. So I start with our 5 pillars. If you go to our website, we will tell you what we think are the 5 most important impact areas where we see Lean make a difference. The first of these is formal mathematics. The second is software and hardware verification. The third is verified software development. The difference between software verification and verified software development that I'm trying to get at here is software verification usually means you take a program you've written in a different programming language, import it into Lean or another theorem prover in some way, verify something there, which then tries to tell you something about the original program. Whereas verified software development, the idea is you write a program in Lean, prove that it's correct, and then usually run that program in its compiled form. Next, we have AI research in both mathematics and computer science. And finally, we have education methodologies, again, in mathematics and computer science. And this is, of course, not all of these things the Lean FRO actually works on itself, but these are the things that we see where we think Lean can be used as a tool to advance the state of the art. Of course, Lean is an open source project. Everyone is happy to use it for whatever they want, and in no way are they constrained to what we think Lean could be useful for. When you download Lean, what do you actually get? This maybe calls back a bit to Manuel's talk from yesterday. You get a dependently typed programming language that can be used as an interactive theorem prover. And you get the components that entail. So we have a parser, elaborator, a kernel, we have a compiler, and we have a runtime that enables actual execution of Lean programs. But that's not the only thing you get. You also get a language server, which is used by the various IDE extensions that are provided by us and by the community. You get the tactic framework and then some tactics to do proofs in. There are very simple ones like exact. There are somewhat simple ones like rewrite. And then there are pretty advanced tactics. 2 examples here are grind and BV decide, the first of which is an SMT solver inspired tactic. And the second one is our decision procedure for bit vectors, which is based on importing unsatisfiability proofs from an external set solver, which we also ship as part of the distribution. You get the meta programming framework, which you can use to write programs that inspect Lean itself, and of course also to write things like tactics. And finally, you get the standard library. Of course, these are not all, so these are the things that you find in the Lean repository and that you get when you download Lean. Of course, there are more artifacts that are considered part of the inner Lean system. So we have things like the VS Code extension or our document system Verso, which are not mentioned here, but still. So what is the standard library? It is what makes Lean into a truly general purpose programming language. It is also what gives you really the basic tools you need to verify things like mathematics or software using Lean. And it is, from our perspective, a public API, something that we want people to use, something that we offer to people with all the responsibilities that entails. Like everything that's part of Lean, the standard library is developed principally by the Lean FRO team, but with contributions by the community, and compared to, which is true for all of Lean, but specifically true for the standard library, where we really want and welcome external contributions even more so than for other parts of the system, maybe. Okay, so this is somehow a very abstract definition. So let's just look at what's actually there or what will be there. And we have 4 sections. The first one, core types and operations. We start with the really basic stuff like true or bool or option. All of the things that you really need to get the theory off the ground. Next, we have numeric types. So that's natural numbers, that's integers, that's also floating point numbers. What I should say in the beginning, of course, the standard library contains 2 things. It contains proofs, and maybe first it contains code, and then it contains proofs. And not all of the things that we will be able to, that we include in the standard library has proofs, or maybe will have proofs in the near future. But everything this specifically is about things that interface really with the operating system. Everything else we want people to be able to use who do verified software, and so we want to ship proofs. The next thing is containers. So there you have your list. Maybe option also counts into this. We have our arrays, and we also have a vector or fixed size array. We have also more complicated data structures, specifically associative containers, so we have hash maps in various variants. So we don't just have a hash map, but we actually have, I don't know how many by now, 8 or 7. So we have a dependent one where the type of the value is allowed to depend on the key. We have a normal one, we have a hash set. Then we have variants of these that are safe to use in nested inductives. And then we also have extensional variants of these where the logical equality really corresponds to equalities as abstract associations. Some things, and we have also the order variant. So we have basically self-balancing binary search trees, again, in all these variants. And we have a bunch of lemmas about these. So these are not, and maybe this is something that we will also come back to later. These are not like toy or proof of concept implementations, but these are implementations that we want to be robust, we want to be complete. So we really provide every variant that we envision our users being able to use. And we really want to provide a broad, good interface with dozens of operations, and we want full lemma coverage. So we're already with these 14 associative containers, we're talking thousands of lemmas. In the future, there are some more containers that we would like to add, for example, double-ended queues, which we don't have at the moment. Next, we have strings and formatting. There we are actually doing a lot of work right this very moment. Hopefully by the end of the year, we are expecting to have also very nice lemma coverage for people who write programs using strings. Next, on the language construct side, so these are really things that allow you to program better with Lean. We have ranges and iterators. So whatever type you have that you are somehow able to enumerate over, you can use in a range. We have an iterator library which allows you to process streams of data in a way that is uniform across wherever the data comes from, is efficient at runtime, and can be used in verified software. So there are lemmas available there. We have the kinds of ordering infrastructure that you need when doing software development. Of course, Mathib has a much more comprehensive ordering library, which is geared more towards the mathematics side. So we're not really competing here. We are providing something for a completely different use case. We have the whole basic monad infrastructure that is used when doing functional programming. Then we have some slightly more standalone libraries. random numbers don't exist yet, but will exist once we get to them. Date and time library we do have, so we have a bunch of, actually a very broad library for timestamps, for durations, for instance. We have lots and lots and lots of formatting. We have many things that appear in ISO 8601 and that make it hard to sleep at night. And then finally, we have operating system abstractions, which are the things that we really provide runtime support for, which are otherwise hard to get. So we have a bunch of primitives for doing concurrency and parallelism, synchronization. We have asynchronous I/O. So you can wait for data without blocking. You can have multiple sources of data and race for the first one that becomes available. Things like that. We have a bit of things to help with the foreign function interface, and then something that has existed for a long time already, but which we are going to completely overhaul. Probably also are or some of which we already have completely overhauled, and some of which we are going to completely overhaul are access operating system primitives like the environment, like the file system, like to information about our own process or spawning other processes. And one thing that's also coming up but doesn't exist yet is a library for internationalization and locales. Okay, who is this all for? Everyone, actually. There are things in there that are so basic that basically everyone will interact with them. We have like natural numbers in there, which are difficult to get around in a system like Lean. So when we work on this stuff, we really try to think about everyone who interfaces with the material we provide. More specifically, we subdivide into smaller groups to make sure that we specifically address their needs. So we have programmers, which again subdivide into people writing software, which may be verified, or which they may want to verify. People doing meta programming, writing tactics or running analysis of their Lean projects, which are of course in a way just normal functional programmers who are doing a lot of heavy monadic processing. We have the Lean developers themselves. Remember, Lean is probably or surely, okay, no, it's not the largest Lean project, but it's the largest Lean program. I think that is so far safe to say, with probably about 1 million lines of executable Lean code. We have library authors who want to make sure that their users again have the tools they need to provide to do great work. Then we have MathLib users, so both MathLib developers and MathLib users, and everyone who lives downstream of that. We have people doing software and hardware verification who we also of course want to target as much of the standard library as possible. So if you're importing code from a different programming language, you're probably going to have some kind of Boolean type. You're probably going to have some kind of 32-bit integers and things like that. And we don't want people doing this to have to think about 32-bit integers themselves. The standard library should come with a great 32-bit integer development that works both when working when writing Lean programs that are interested in that, and also when verifying software using 32-bit integers in a different programming language. And finally, if you're thinking about using Lean but are not sure yet whether it's the right fit for you, then of course it's very important that you have all the tools you need to accurately evaluate whether Lean provides the tools that you need. So we want this the relevant parts of the standard library to be sufficiently visible that you know what you need is there. Okay, so what are the goals? We want it to be useful for doing real work, whether that's formalizing mathematics, whether that's writing real software. This is we are we need the standard library to be able to support people going beyond just experiments. We need to support people working until project completion, not just for the first half. We want it to be extremely high quality. Here's a long list of adjectives that we want to be true for the standard library, more or less, roughly ordered maybe by order of importance, but maybe not. But I really do think comprehensiveness and consistency are two of the most important things. And here we may be making a bit of a difference between the various application areas of Lean that I discussed in the beginning. We want, when you install Lean and nothing else, you should already have most of the things or all of the things you need to write software and to verify software. This is not true for mathematics. It's usually unrealistic to do mathematics without using something like Method. But specifically as a programming language, if you view it as a programming language that allows you to writing proofs, you should not need to go searching for all of the things that should have been there in the first place. You wanted to install Lean and write your first program and prove it correct, all without taking on a single dependency. Which leads me to what our goal is really here, or our long-term vision. We want formal verification, whatever that means. I think this is a very broad term. We want it to be economical and commonplace. So what we have right now, most people using proof assistance are in one way or the other enthusiasts, and are willing to sit through imperfections of the system, and because they enjoy what they're doing, they're willing to work through the difficulties. They're willing to overlook things. What we see in the future is people being at work to be told to use Lean, and if the system is annoying to use, if it puts roadblocks in your way, then this will not happen, or at least not happen without protest. So the bar is really higher, I think, than what anyone can provide at the moment in terms of usability. So it's not about whether this can be done, but whether it's easy and whether I feel really productive doing it. So what do we need for this? We need no missing material, which is so usually when you work on something, you discover missing materials. That's really upstream of what you're actually doing all the time. We don't want people who are verifying their code to go back and prove something about lists. This is not good enough. There should be no inconsistencies or other paper cuts. I shouldn't wonder, okay, why is this now like that, even though this other thing is like this? I should never, for maybe this reason or maybe any other, struggle to find something that is actually there. So what we really need is we need to find some way to systematically approach the problem of how do we raise the quality of our library. And I think we need to, and I think specifically in the standard library, we need to do it much more so than other libraries like Method. Yeah. So we need tools, and there are some great tools. There's CI, which in its most basic form makes sure that the code at least compiles, which is an important bar of quality to clear. There are linters, which make sure that my code follows a certain set of predefined rules, which is really important and which we should do much, much more than we are currently doing. Michael said the same yesterday, and I fully agree with him. We have code review, which is also great. And it works both well as a quality assurance tool and also as a communication tool. But there are gaps in this. there are things that none of these can see. Linters only work for things where I can write down a rule and I can write it down so precisely that there is a program that checks it. In code review, at least the way I get at least it's presented in something like GitHub, focuses on the things that change and the things that are there. But it doesn't, by doing this, it basically directs the attention away from the things that did not change and that are not there. So if I have, and what this invites, what that invites is introducing inconsistencies into the code base. So for example, you introduce a new lemma, you get a pull request from someone, or maybe from yourself, that adds a theorem about some kind of container. Well, we have 20 containers. Does that theorem exist for the other containers? Does it have the same name? Is it stated in the same way? Should it have been added for the other containers? Like GitHub will not show me this. And maybe I remember to do it, great, but there are actually many axes along which I could do this. So maybe there are also on the containers related operations. So if I add or change a lemma about one operation, then I should also add or change it for the other operation. And there are, and it's really easy to miss things there. So we need, so the things we have are really good and important, but we need more. Why am I showing you this picture? I am showing you this picture because this is what I see when I think about Lean Standard Library. This is a forest, as I'm sure you know. and maintaining something like the Lean Standard Library is a bit like forestry, is what I claim. So this forest, it's an organic thing. It lives on its own. If I just leave it sit there, it will do something. It will change. But on the other hand, I, as a human, I have an interest in seeing this forest develop in a certain way. And if I want this, then I need to put in the work. And this thing is and where this all starts is, this thing is large. I can't just sit somewhere and just wait for things to happen, or wonder whether something happened. I need to like regularly look everywhere and see what is the current status. And the other thing that's also similar is I have a lot of projects that I know I need to do. At some point, some of them are more urgent than others, and I need to properly prioritize what I work on in which order. So here's what I claim to be true, specifically for the Lean Standard Library, and it's completely different for other libraries. I claim that quality assurance will always have a manual component. You should automate it as much as you can, but there will always be things that you will just have to check manually. So you need tools that are flexible enough to support assuring quality in some kind of manual way, tracking your work, but at the same time they need to allow you to automate away your own work when the time has come. Not all rules can be fully formalized. Many rules have exceptions. Here's also something. What I described earlier in many ways describes an incredibly high bar of quality, and you need to be aware, or you need to be sure that this is actually something you want, and you need to be sure that you're willing to put in the enormous work that it will take to achieve this. And I think for many libraries this is not the case, but for the standard library, where really also the first impressions of users depend on this, I think this, and also the long-term productiveness in the same way, this is something that is desirable. And finally, what I was hinting at earlier, we need to know what the library actually looks like. And we need to know how it changes as the library evolves. And And this is for two reasons. First, you will get and you want to get contributions by anyone, including yourself, and you want to merge these because you want to make progress, but you also want to at least be aware of what the repercussions of merging a PR are. You want to know, if I merge this, what gets added to my to-do list, and you also need to have the information to actually add that to your to-do list. If you introduce new defects into your library, you need to be aware of this. And the other thing is, you need some way, you want some way, I mean, you have a certain amount of time in your day, and you need, I want to be able to make statements about the library, such as for a certain part of the library, for a certain kind of thing that, for a certain kind of defect that could be there. I know all of the defects that are there, and after working on it, I can say, okay, there are now no more defects of this kind in this section of the library. So I want to be able to make statements about the library that have some that I know are true. Okay, so how did I try to make progress towards this? Here's a spreadsheet that I made when I was working on the hashmap library last year. So here the question was, okay, for all of the various operations on the hashmap that we have, are the relevant lemmas available? So here is just a manual spreadsheet that I made that built the whole matrix of operations, of modification and query operations, and I filled in by hand how the relevant lemma is called that I added, and this is the blue, a justification, or why the fact that there is no lemma needed to cover this interaction, and in some more complicated cases with a small justification why that is true. Simple stuff, and then and now we're already starting to see these various axes. Then I can go maybe along this axis and see, okay, does the naming of all these lemmas look right, for example? Okay, that's nice. The next step came when when we were working both on the date and time library and also on the finite type libraries. There we had so this is just about operations, not even about lemmas, but there we needed to make sure that all the right operations were there for all the types and that they had the right names. So yeah, here you can see, especially the data type library. I mean, this goes on for hundreds of lines, and this is also going on for hundreds of lines. The surface is just huge, and this is where I already started using meta programming. So here, what really happens is you have a lean program that generates a CSV file that I can then import in Google Sheets and analyze. But then, of course, you want to be able to group these operations, so I reorder the rows, but then maybe I found some problems, fixed them. Now I run my meta program again, but now it spits out the rows in a completely wrong order again because I reordered them. So in order to establish this feedback loop, I actually need to be able to re-import this ordering information into my lean meta program. So what actually happens is this is a lean program that generates a CSV which contains a Google Sheets formula, which then spits out lean code again. So clearly this won't scale. Okay, so next step, here we drop Google Sheets and instead had a little prototype React application. And now you can see the thing slowly starting to take shape. So this is, so here we have the lemmas, the table relating different operations on different types again. Here we have the lemma table again, and now I can really, I can already see here the so I get these little numbers which tell me for the different data types that I have, of which there are many, for these kinds of operations that I'm relating, how many lemmas are there. And then I can already see, okay, I can basically try to also try to spot patterns. So here I see in this row is two weird outliers, namely this one, and here this 0 there. So probably I should look at that. Maybe there's something wrong there that I where I forgot a lemma. So that was the idea there, but this was still somehow, and of course all this data is collected again by a lean meta program. But this is still somehow a one-off solution, which isn't really library scale. Here we have the same thing again, just larger, this time for the finite types. Here now you can see again also these colors where I've manually marked the things that I've already looked at. And being able to persist this is of course really important, because going through a table like this takes multiple days. So you need to know where you left off and what you're still missing. And finally, packaging this up into a real tool that we can deploy. The tool is called Growth, and it's this time it's all of the ideas from before combined, but into something that can really handle an entire library. And the basic question, and this is also has been a long time coming from what I've been telling you. What do we know? This is what the tool is trying to answer. If I've and the really important thing, if I've looked at something and I decided it was good at one point, what can be the things that can change in the library that make the statement no longer true, so that I need to revisit something? So what the tool allows you to do is it allows you to describe the shape of your library in Lean declaratively, but with as much metaprogramming mixed in as you want. And then you get a web user interface that you then allows you to analyze the state of the library, make annotations, mark things as looking good or as to-dos. And then you can either right now or later work on them and update the state as required. And importantly, whenever you enter some piece of information into the system, if a PR comes along and changes that the thing you looked at to come to a certain conclusion, then in the PR we get a notification that this has changed. So I might show a few pictures. So this is a simple. So this is how describing the library looks. So for example, here we list all of the associative containers we have, just their names, and then we say we want, for example, the table that associates all the query operations of these associative containers to each other. And then we say, okay, to get for a certain container name, to get the declarations, then we basically take all the definitions in the namespace, and then we can also unify, take the union with some other kind of thing. And for example, here for the associative containers, we also have this get-a-lem operation, which doesn't live in the namespace of the container. So we add that there, so we can select it in the web UI later. And then when I can basically hierarchically create a bunch of these things and create a large nice tree that somehow should reflect the state, the shape of my library. And then what I get is this web UI, which you can see here. So right now it's looking a bit bare bones because we're still at the very start of actually filling it with data. But you get these collapsible sections, which you might recognize reflect exactly the shape of the library that I described to you earlier. And then I can open things more and more. And at the bottom here, I can get these. I get these various elements. So these tables here associate the operations with each other, and then I get these other tables, which then are about lemma coverage for certain situations. And as I said, it's extremely flexible. So for example, I can I also have this assertion thing where I can basically write an arbitrary meta program which just spits out, okay, a failure or a success, and the tool then keeps track that this assertion stays true. as changes to the library come. And then I can open up these widgets, and then I might get something like this, which, as you can see, looks very much like the prototype I showed you earlier. So here we have a whole bunch of operations on our various associative containers, and then here you get these tables for the lemmas again, and then, for example, here you can already see again this 0. There's probably something up there. We should look into this. And then when you get a PR, you might get a message like this, which then tells you, okay, some things that you thought were true about the library are no longer true. And right now you get just these primitive IDs. In the future, we will link directly to the relevant widget. But if you, then you can have a look, and then you will get a dialogue like this, which will tell you, for example, you looked at the statement of this, or you looked at the signature of this function, but and you said this was good, but now the PR changes the signature to this. So here, for example, you see the binder types changing, and then you need to decide, okay, is this still good, or do we have a problem here? And in this case, for example, we do have a problem here because the old version was actually the right one. And similarly, so this is just about the single declaration, but also if we somehow lose consistency across some kind of axes, we will get a similar result. Okay, so maybe to just give a tiny bit about how this works behind the scenes. So the way we store the data in the background that you enter in the web UI is actually Lean. So this is auto-generated Lean code exported by the web app, and then we have a somewhat complex diagram that shows how the whole thing works. But basically, basically, Growth is just a large Lean program. It ingests both the data you had previously exported, your description of the library, and the actual library, how it looks today, builds an executable, which then runs and does all the analysis, prints out a JSON file with the findings, and then from that we both detect if something has changed and post a PR comment, and we build the web application, which we can then upload to Netlify so that we can look at it as we want. And then the user looks at the web application, decides whether anything needs to be done, and saves the new state into the Lean repository. And of course, maybe they want to change the standard library in response to the findings, which also lands in the Lean repository. So once all the changes are there, you just commit, push, and the whole cycle starts again. Yeah. So this tool is working. So what we're currently in the process of is really ramping up its use. We have some usability things we still want to address, but it's already installed in the Lean repository. It's already in use today. And throughout the rest of the year, we will really feed it with more data so that it supervises basically the entire Lean standard library.
Thank you.
Can we use this for other libraries?
In principle, yes. So these are separate repositories. So there's a pre-packaged repository containing all the GitHub actions that you need to run this for your own. You do need a Netlify account or somewhere else to host the web app, but this is free on Netlify unless you're really hammering it with requests. I think the more fundamental question is, is this really the kind of quality that you need in your library? Because doing like maintaining quality to this bar is an absurd amount of work, and it's not going to scale infinitely. So the standard library is 250,000 lines at the moment. It will maybe scale to about double of that in the coming months and years, but it's never going to reach the scale of something like MATLAB. So if you were thinking about using this in something like MATLAB, maybe for the really low-level things like FinSet, this could work, but it's never going to work in the more mathy parts of math.
I was about to ask the same thing for a very localized question that I have. I guess you answered that already. Thank you.
I was wondering if you took any inspiration or learned any lessons from the standard libraries of other languages.
So we looked, and maybe I'm bad at searching, but I didn't neither speaking specifically about this quality assurance aspect. I was not able to find anyone else attempting quality assurance at this level. Of course, for the standard library design itself, we take inspiration from lots of different places. So specifically for the more programmy parts of the library, we very liberally take ideas, inspirations from Rust, from OCaml, from Java. We try to, of course, also take into account what standards bodies have to say, specifically for things like for the date and time library. We looked at what the Unicode consortium on locales has to say. We looked at ISO 8601 and things.
Can you comment a bit on how this interact with just more traditional unit tests that you have in the Lean4 repository and STD?
Yeah. So the rule is very simple. Everything that can be handled by unit test or linter should be handled by unit test or linter, because it's much more immediate feedback. Especially if you're saying if this rule is violated, we definitely don't want to merge the code at all. What Grove is really good at is organizing manual work, and it's really good at tracking things that you know are not right, but that you're just not going to do something about right now. So with Grove, basically, I can push all of my work as far into the future as I want. I will never forget that something is problematic. And even for these invalidations where I know what I thought to be true is no longer true, I can even wait with these as long as I want. The system will never forget to tell me that I have to look at this at some point. It will give me statistics about, okay, these parts of the library have these kinds of number of defects, so that I can specifically see where I maybe have more work to do than other parts. And also, we don't know how often this will happen, but if a problem just resolves itself without me ever having looked at it, then the system will recognize this as well.
So that's more flexible than just creating a GitHub issue and just let it.
Yeah, I mean it's connected directly to the data. It's fully automated. It will tell me exactly this used to be like this, now it's like this. What should we do about this? Yeah. And of course, it's versioned together with Lean, so I can branch it. I can look at the status as it is in a PR compared to how it is on master, things like that.
I also had a small question about the data type. So you've told us we have 8 kinds of hash map or something like this, but does it mean that for string, this will be like in Rust, where you never know which kind of string you want, and because they have 10
Rust has basically 2 strings, and we also have now basically 2 strings. We have the one that actually contains the data, and one that's just a view on some data wherever that may be. But we try our best that you never notice the difference unless you really try to see it.
Perhaps last question.
So maybe kind of a follow-up on this is that, I mean, you seem to have the hope that you can have one version of, for instance, the natural numbers that's good for everyone, but like it's a very, very high bar. Like the chances that the mathematicians want the same natural numbers as the programmers, as the whatever, like are I think quite low. Like, do you have any idea how to deal with this? You just have different data types and then people pick whatever they want, or like, how are you going to address this?
So for the natural numbers, no one has ever asked us to change the definition of the natural numbers, and I'm not aware that anyone has ever tried to give a competing definition of
I mean, I can
numbers.
say it's like in ROP, for instance, there are very competing definitions of the unary natural numbers, which the mathematicians we use all of the time because you have induction, it's nice. And you have Z, which is binary natural number, which is the thing you use whenever you want to do any computation, because computing with unary natural numbers is horrible.
Lean has special support for natural numbers in the kernel.
Okay.
But I get your general question, and the answer is when in doubt, the standard library will try to think from the perspective of a software developer. We think the method community is generally the better place to put definitions that mathematicians like in case there is a divergence. And of course, we and the standard library team tries to cooperate with the method community as much as possible. I hope we've been good about this in the past year. If not, please let me know. So we will definitely try to make sure that if there are competing definitions that are connected as well as possible. Also.
Maybe as a follow-up to this, even programmers may have different requirements, right? If you write verified software, you might need data structures that are easy to verify, which may be not quite as efficient. But if you write just programs that you don't verify, you want the most optimized version of the data structure, which can be very hard to prove. I suppose all of those data structures with different characteristics, or what's the plan there?
So our approach so far has been write the most optimized version and put in the hard work to make it as easy to prove things about for downstream users as we can.
Do you think that's going to be possible?
We'll see. I mean, the standard library is not going to grow indefinitely. We're going to have. I think we've done well enough for the associative containers. We're only going to ever add at most a handful more data structures, and then of course you have things like algorithms. You're going to have. We already have an implementation of KMP. We're going to, and that is written for performance. We're going to try very hard to provide lemmas about this implementation of KMP. We have plans, though not super immediate, to really put in the work, do proper introspective hybrid sorting and verify that instead of just giving a simple, I don't know, merge sort and verify that. We are so by specifically limiting the scope of the standard library, we are specifically saying those things that we do provide, we will try our hardest.
Okay, so thank you. And so the last talk will be remote by Justin Asher. So Justin, you can share your screen, hopefully.
Right. Maybe you need to stop sharing here.
No, okay, it should be.
Can you see my slides?
Yes. So just a moment.